So hi everyone, and today's lecture we are going to see what is amplitude modulation and demodulation, and also we are going to implement using the MATLAB. So first of all, let us see what is the definition of amplitude modulation and demodulation. So amplitude modulation is defined as a process in which the amplitude of the carrier wave C of t is varied about a mean value linearly with a baseband signal m of t. So, in other words, we can say that the amplitude of the carrier is varied in accordance with your message signal. So, where we use this amplitude modulation and demodulation techniques. So, let us see the communication model. So, in the communication model, if you look into the amplitude modulation and demodulation techniques are used in the modulation technique is used at your transmitter and a demodulation technique is used at your receiver. So we'll see what are the basic things which are there and what are the basic idea about how to implement the amplitude modulation and demodulation. So here to implement your amplitude modulation technique, so we want a message signal. We want a message signal and a carrier signal. So when a message signal and a carrier signal is given to a modulator, so we'll be getting an modulated output. So with this little bit of information, we'll move forward. What are the message signal and what is the carrier signal and what is the standard equation that we can generate for your modulation, amplitude modulation? Let us see. So here to implement the amplitude modulation and demodulation, we require a message signal. So the message signal is defined by m of t is equals to am cos 2 pi fmt. It requires an amplitude of message signal. We require the frequency of message signal, and also we require a sinusoidal carrier wave that is defined by c of t is equals to ac cos of 2 pi fmt. FCT. So we require the amplitude to define the amplitude of your carrier wave, that is AC, and also require a carrier frequency FC. So when we give the message signal and a carrier signal, message signal and carrier signal to a modulator, then we get the modulated wave output, which is having a general form that is S of t is equals to AC into 1 plus Ka m of t into cos 2 pi fct. So here, what we are doing is we are considering the phase to be 0. Otherwise, the m of t is defined as am into cos 2 pi fmt plus phi. And here c of t is also ac cos of 2 pi fct plus phi. So as we are considering that the phase is assumed to be 0, so we are writing m of t is equals to am cos of 2 pi fmt and c of t is equals to ac into cos of 2 pi fct. So when we modulate the most general form of the equation, what we are going to get is s of t is equals to ac into 1 plus k m of t into cos 2 pi fct. So what is this k? K is called as amplitude sensitivity, and we are going to, based on this ka value and the modulation index. Here, we get three forms of modulated waveform. One is for under modulation, the other is for your over modulation, third one is exact modulation. So let us see what is the under modulation, what is exact modulation, and what is perfect modulation. So whenever, as we have said, that Ka is the amplitude sensitivity, when we measure the modulation index, that is the amplitude of Ka m of t, if it is always less than unity, that is mod of Ka m of t, which is less than 1 for all values of t, then, or in other words, your modulation index, that is Ka into Am, if it is less than 1, then the modulation, whatever we say, it is called as your under modulation. Okay. So if if your mod of Ka m of t, if it is greater than 1, the mod of Km of t is greater than 1 for all values of your t, then the carrier wave becomes over modulated. Over modulated means that results in the carrier phase reversal that you can see here. There is a carrier phase reversal which occurs for all the factors, that is 1 plus km of t when it is crossing your 0. So there is the envelope distortion which is going to occur. So that is, indirectly we are saying that the modulation index, that is Ka into Am, if it is greater than 1, then the wave will be over modulated. So next comes is your exact modulation. So in exact modulation, what happens is if your Ka m of t is equals to 1, the carrier wave will become perfect modulated or exact modulation. That means your modulation index is equals to 1, then you'll get a perfect modulation. You are going to get a perfect modulation. So now let us see how to write the program using your MATLAB for this amplitude modulation and demodulation. So, so here is the program what we are given for your amplitude modulation and demodulation. So first of all, what we do is here we will be clearing all the variables, figures, and consoles by giving the function, that is close all, clear all, and CLC. After that, we are going to set the parameters. What are these parameters? So these parameters are which are going to be used in generating your carrier wave, message signal, and modulated wave. So for that, first we are going to define a sampling frequency. So this sampling frequency is used in getting the what we say time vector, and we are taking the frequency of your message signal to be 20 hertz, and which is the low frequency signal, and we are going to take the carrier frequency to be 500 hertz, which is a high frequency signal, and defining the amplitude of your message signal to be 1, and defining the amplitude of your carrier signal to be 1. So once the parameters are defined, then we'll go for generating of the signals. So before generating of the signals, we'll see how to define the time vector. We are going to define the time vector. T is equals to 0 is to 0.1 into Fs by Fs, where 0.1 is the time interval what we are defining, and the duration of your time vector is given as zero point 0.1 into your sampling frequency, whatever we have defined earlier, that is sampling frequency of 8000. So the total value, that is when division is done by Fs, the scales the time vector by sampling frequency, converting the time instances from sample index in actual time values in your seconds. So this is how we are going to define your time vector. So starting value and the interval is 0.1, and 0.1 into Fs will give the time vector, and it is finally converted into your seconds by dividing your sampling frequency. So now next is to generate your modulating signal. What is modulating signal? So modulating signal is nothing but your message signal, as we have said earlier. So here we are going to define your message signal using M. M is equals to Am into cos of 2 pi FMT. Already we have defined the Am value, and we have also defined the frequency of message signal to be 20. So next, to generate your carrier signal, we are taking a C is equals to, what is that? C is equals to AC into cos of 2 pi FCT. So we have defined the carrier wave amplitude to be AC, which is equals to 1, and we have also defined the carrier wave frequency FC is equals to 500. Already the time is defined as 0 is to 0 0.1 into Fs by Fs. So now we'll proceed for how to do the modulation. So as we have said that there are three cases in your amplitude modulation, and one is the under modulation, the second one is perfect modulation, third one is over modulation. Let us see, we'll implement one by one. So first we'll see to implement your under modulation. So already uh, we have said that the amplitude sensitivity is a factor which is going to decide which is what we say decide the whether the wave is under modulated or over modulated or exact modulation. So here we are defining the amplitude sensitivity as 0.5, and we have also defined the modulation index. Modulation index mu is equals to Ka into Am. That means if Ka is equals to 0.5 and Am already defined as 1, then the mu value will be less than 1. The mu value will be less than 1. Then this, we are defining the standard equation, which is defined as S1 is equals to, that is AC into 1 plus mu into cos 2 pi FMT into cos 2 pi FCT. So this equation, we will get the under modulation. Why? Because my mu value is less than 1. Now, let us see that AM, the amplitude of message signal is 2, then your Ka value, if it is 0.5 only, then the modulation index value, it is 2 into 0.5, which will be equals to 1. So when you have the modulation index is equals to 1, then you are going to get a perfect modulation. We are going to get a perfect modulation. Now, let us see the third case, that is modulation, that is over modulation. So in the over modulation, what we do is, I am taking the amplitude of your message signal to be 5, and your uh, amplitude sensitivity is defined as your 0.5. So when I multiply Ka into Am, the value will be greater than 1. So the value will be greater than 1, and if then your wave is over modulated, then the wave is over modulated. Now we have already generated the three waves. Now how to plot these three waves using your MATLAB? So coming to the plotting of your equations, so here I'm going to plot the modulating, carrier and modulated signal. That is nothing but your message signal, a carrier signal and modulated signal. That is under modulated, over modulated and exact modulated signals. So for that, what I am doing is I am using a function called as subplot. So this subplot of 4 comma 3 is comma 1 is to 3. So I am defining a matrix. Here you can see I am defining a matrix which is having 4 rows, and 3 columns. In that, I am going to plot, what is that plot? We are going to plot here, we are going to plot T comma M, that is message signal. I am going to plot in first row, that is 1, 2, 3. So here I am going to plot your message signal. Once the message signal is plotted, then I am going for plotting the carrier signal, that is subplot 4 comma 3, that is 4 is to 6. That means from here to here. So that I am plotting your carrier signal. So first 1, 2, 3 places I have marked your message signal, and 4, 5, 6, that is 4 is to 6. I am plotting your carrier signal. So plot T comma C, that C represents your carrier signal, which is having a frequency 500 Hertz. So once these two signals are plotted, then I need to plot. So even if you want, you can make the plotting separately by using a predefined function called as figure, and you can get an individual plot for each and every signal, like your message signal, carrier signal, and your modulated signal. We can get separate figures also, but to show all the figures within one block, one diagram, I am plotting each and every figure within the same figure. So here, next we are going to plot. Next we are going to plot the modulated signal. So now plotting of your modulating signal. So for that, what we're doing is we are going for the subplot 4 comma 3 comma 7. That means in the seventh slot, I am going to plot t comma s1. That means what is s1? We have already defined. We have already defined S1. S1. S1 is nothing but your amplitude modulated wave for your under modulation. S1 is nothing but a modulated wave for your under modulation, and S2 it is for your perfect modulation, and S3 for your what we say the over modulation. So S3 defines your over modulation. So this is your over modulation. So here we are going to define already the under modulated and exact modulation. Now third one what we have is your exact modulation. So subplot 4 comma 3 comma 9. So this 9 in the position of 9 we are going to plot your S3, that is plot S3 in the position of your 9, that is over modulated signal, which is having your amplitude modulation index greater than your 1. Okay. Now, let us see the demodulation process. In the demodulation process, how we are going to get a demodulated output. So, if at all you want to get a demodulated output, you need to multiply the modulated signal with your carrier. If you multiply your modulated signal with your carrier, you are going to get a demodulated signal. So as we are taking your S1, so S1 is a modulated signal, that is under modulated signal, which we have already defined, to which I am multiplying with your carrier. Once you get your demodulated signal, then we are applying a Butterworth filter of order order 1. So this order 1 filter we are applying, and which is having a 0.01. This is the cutoff. This is the cutoff, normalized cutoff frequency of your filter. What we are defining it as 0.01. So we are applying a Butterworth filter of order 1 with cutoff frequency, normalized cutoff frequency of 0.001. So then we are defining uh, the filter, that is the wave MR1, the demodulated wave MR1 filter of Butterworth filter, and which is that wave? The demodulated wave is R1. So R1 is a demodulated wave for which I am applying the filter, and that is nothing but your MR1. In the similar way, for R2, that is for exact modulation, we are going to uh, get a demodulated wave, that is R2. R2 is nothing but the demodulated wave into your carrier, and same we are going to use the Butterworth filter. We are going to use the Butterworth filter. Actually, there is no need of always defining the Butterworth filter. Once we have defined, that's enough. So when we define this Butterworth filter, once that is, it can even be used for the other one also. So there is no need of always defining this Butterworth filter. Once you have defined, we can use it. So MR2 represents the demodulated wave of your exact modulated wave, where R2 represents your demodulated filter. So we are applying again the filter for your R2 demodulated wave. And similarly, the demodulated wave for your exact, this is your over modulated. So over modulated wave. So that is this is MR3. Let us define this one as your MR3. MR3. So We are going to define this one as MR3. MR3. So filter B comma A comma R3. So this R3 represents your over modulated. This is your over modulated signal. So once the process of applying the filter and demodeling the signal, then we go for plotting of this demodulated signals. Where we are going to plot this demodulated signal? So already we have plotted 1:3. We have plotted message signal. 4:6. We have plotted your carrier signal. 7, the under modulated. 8, your exact modulated. 9, we have used the over modulated. And in the 10th place, we are going to, that is first row, first column, last row, that is 10. Subplot 4 comma 3 comma 10. So here we are going to use demod of under modulated signal. So plot t comma mr1. So what is this t comma mr1? We have already said MR1 is nothing but the demodulated wave of your undermodulated signal. So we are plotting MR1, that is the demodulated signal, which is after passing through your, it is going to display the signal which is after passing through your filter. Now in the similar way, so subplot 4 comma 3 comma 11. So here in the 11th place, we are going to plot the exact modulated signal, that is plot t comma mr2. So mr2 represents the demodulated wave of your exact modulated wave, and where you have your modulation index is 1, and third one subplot 4 comma 3 comma, sorry, this is 12. So 12. So in this, again this is 3. So plot t comma mr3. So here we are going to have this 2.5. So, when we plot t comma mr3, we are going to get in the 12th position the demodulated wave of your overmodulated wave. Now, let us see how we can implement using directly the MATLAB. So for this, already I have copied the code into a notepad. So now I am going to uh, paste the same program into the MATLAB, and I will show you how the output will be visible using your MATLAB. The MATLAB here I am using MATLAB R2021A. So this is the program which I have already copied. So as we have already seen that program, the small modifications, what we have read, the mistakes over there. So this is MR3 plot 2.5, 1 and 0.5. So R2 and R3, MR2, MR3 and so the same program I am going to copy, and this is the platform. So you can see the program, whatever we have explained, I have copied into the MATLAB. Now run the program. Before running the program, we need to save the program. I'm saving here with experimenter 2. So now you run the program. So whatever we have said, so in the first 1, 2, 3, we have plotted the modulating signal with a frequency of 20 kilohertz, and 4 to 6 we got a carrier signal which is of 500 hertz, and under modulated wave in 7, and exact modulated in the 8th position, and over modulated in your 9th position. The similar way, the demodulated 10, 11, and 12 for your under modulated, exact modulated, and over modulated. Thank you.